Gas engineering is a multidisciplinary field that integrates reservoir engineering, fluid flow, thermodynamics, production systems, processing technologies, and transportation infrastructure to ensure the efficient development and utilization of natural gas resources. As natural gas continues to play a critical role in the global energy transition, engineers must understand the complete gas value chain. From subsurface reservoirs and well deliverability to processing, transmission, storage, and emerging applications such as hydrogen storage, carbon sequestration, and geothermal energy. This course provides a foundation in gas engineering principles, focusing on gas properties, reservoir behavior, production performance, deliverability analysis, surface facilities, and engineering decision-making. Emphasis is placed on both traditional gas developments and modern energy systems that support a lower carbon future. By the end of this course, you will understand the fundamental concepts, engineering methodologies, and industry challenges that govern natural gas production and management across the energy sector. The oil and gas industry operates through an integrated value chain that transforms subsurface hydrocarbon resources into products that support modern society. The process begins with exploration, where geological and geophysical methods are used to identify potential hydrocarbon accumulations. Once commercially viable resources are discovered, production activities are undertaken to extract oil and natural gas from the reservoir. Produced hydrocarbons are then transported through pipelines, shipping networks, and other infrastructure to processing and refining facilities. While crude oil is refined into fuels and petrochemical feedstocks, natural gas is processed to remove impurities and produce marketable gas products. These products are subsequently utilized across multiple sectors, including power generation, industrial manufacturing, transportation, residential heating, and chemical production. Understanding this value chain is fundamental because engineering decisions made at one stage can significantly influence performance, economics, safety, and environmental outcomes throughout the entire system. Flaring is a critical safety and operational practice used to dispose of excess hydrocarbons during production, processing, and emergency situations. However, the environmental impact of flaring depends largely on gas composition and combustion efficiency. Natural gas is primarily composed of methane, with smaller quantities of ethane, propane, butane, and other hydrocarbons. It may also contain non-hydrocarbon components such as carbon dioxide, nitrogen, hydrogen sulfide, and trace impurities. When combustion is complete, hydrocarbons react efficiently with oxygen to produce carbon dioxide, water vapor, and heat. Complete combustion is characterized by a stable flame, high energy efficiency, and minimal pollutant formation. In contrast, incomplete combustion occurs when oxygen availability, mixing conditions, or gas quality are inadequate. This can result in the formation of soot, carbon monoxide, unburned hydrocarbons, and other pollutants, reducing both combustion efficiency and environmental performance. Therefore, flare performance is governed by two key factors: gas composition and combustion efficiency. Understanding these factors is essential for optimizing flare design, improving operational performance, and reducing greenhouse gas emissions. The natural gas industry consists of three major segments: production, processing and transmission, and distribution. The process begins at the production stage, where natural gas is extracted from underground reservoirs. At the surface, separation facilities remove produced water, condensates, and other associated fluids before the gas enters the processing system. During processing, impurities such as carbon dioxide, hydrogen sulfide, water vapor, and other non-hydrocarbon components are removed to meet pipeline and market specifications. Valuable natural gas liquids may also be recovered during this stage. The treated gas is then transported through high-pressure transmission pipelines. Compressor stations are strategically located along the pipeline network to maintain pressure and ensure continuous gas flow over long distances. Gas may also be stored in underground reservoirs or liquefied natural gas facilities to balance seasonal demand and enhance supply security. Before reaching consumers, odorants are added to improve safety by enabling leak detection. The gas is then distributed through local pipeline networks to residential, commercial, industrial, and power generation sectors. This integrated system ensures that natural gas is produced, processed, transported, stored, and delivered safely and efficiently from the reservoir to the end user. Methane leakage represents one of the most significant environmental challenges associated with natural gas systems. Although natural gas is often considered a lower carbon fuel, Methane is a potent greenhouse gas with a global warming potential significantly higher than carbon dioxide. As shown in this figure, methane emissions can occur throughout the entire gas value chain, including drilling and completion activities, production facilities, processing plants, transmission pipelines, distribution networks, and end-use systems. While individual leakage rates may appear small, their cumulative impact can be substantial. Even modest losses reduce the environmental benefits of natural gas and contribute directly to climate change. Consequently, reducing methane emissions has become a major industry priority. This is achieved through improved equipment design, leak detection and repair programs, continuous monitoring technologies, operational best practices, and stricter regulatory requirements. Effective methane management improves environmental performance, enhances operational efficiency, preserves valuable product, and strengthens the long-term sustainability of the natural gas industry. Natural gas is one of the world's most important energy resources, accounting for approximately 1/4 of global primary energy consumption. Alongside oil and coal, it forms the foundation of the modern energy system. The figures illustrate 3 important global trends. First, natural gas has become a major contributor to the global energy mix due to its abundance, versatility, and relatively lower carbon intensity compared with coal and oil. Second, natural gas resources are unevenly distributed around the world. Countries such as Russia, Iran, and Qatar possess some of the largest proven gas reserves, influencing global energy security, trade, and geopolitical relationships. Third, global energy demand continues to grow, with natural gas consumption increasing steadily over recent decades. This growth is driven by electricity generation, industrial development, petrochemical production, and the transition toward lower carbon energy systems. As the energy sector evolves, natural gas is expected to remain a critical bridge fuel, supporting energy security while enabling the integration of renewable energy, carbon management technologies, hydrogen production, and other emerging low-carbon solutions. This slide illustrates the journey of natural gas from the reservoir to the end user and highlights the complexity of the natural gas value chain. Natural gas is produced from underground reservoirs through dedicated gas wells or in association with oil production. Following production, the gas undergoes separation and field treatment to remove water, condensates, and other unwanted fluids before entering the processing system. At the gas processing plant, impurities such as carbon dioxide, hydrogen sulfide, and water vapor are removed, while valuable natural gas liquids, including ethane, propane, and butane, are recovered. The treated gas is then compressed and transported through transmission infrastructure to storage facilities and consumers. From a market perspective, natural gas is supplied to several sectors, including residential, commercial, industrial, and power generation applications. Among these sectors, electricity generation and industrial use represent major components of gas demand due to their significant energy requirements. This integrated supply chain demonstrates that natural gas is not simply a fuel extracted from the ground. It is a processed energy commodity requiring sophisticated engineering systems for production, treatment, transportation, storage, and final utilization.